The interaction of light with matter can be complex, as light sometimes exhibits behavior that can be best described by that of a particle and sometimes by that of a wave. This principle is called the wave-particle duality. This duality is not limited to light, but is in fact true for all particles, including matter. Wave-particle duality is a very intriguing property of quantum mechanics, and its interpretation has been subject of many discussions. For this course, however, we will just accept that depending on the situation, light might behave as a particle or as a wave. As an electromagnetic wave, in fact, that propagates through an oscillation in an electric field and an oscillation in a magnetic field, as shown in this illustration. The behavior of electromagnetic waves are described by the Maxwell equations, which are rather complex and outside of the scope of this course. Later in this course, we will qualitatively consider how the electromagnetic wave behavior is used in solar cell design. The learning objectives of this video are to understand how some behavior of light is best described by that of a particle and to be able to relate the different properties of a light particle. We will introduce some important definitions to express light incident on a surface, like that of a solar cell. The final objective is to understand how a flux of light particles is related to the total power incident on a surface. The particle behavior of light is well illustrated by the photoelectric effect. The photoelectric effect is demonstrated in a simple movie I found on YouTube. You see here an electroscope. This is an instrument to demonstrate the presence of electric charge. Using static electricity, a bar is charged and the pointer indicates the amount of charge. At the moment, the metal bar is negatively charged by a large amount of electrons. The only way to discharge the electroscope very fast is by putting it in contact with other materials. For the moment, we are waiting until the mechanical fluctuations of the electroscope dampen. Now the bar is illuminated with the lamp. What we see is that the light is able to remove the charges very fast by exciting electrons from the metal. Classic electromagnetic theory predicts that changing the intensity or the wavelength of the incident light would affect the rate at which the charges are removed from the metal bar. Experiments show, however, that the incident light only excites electrons from the metal when the wavelength of the light is below a certain threshold. This means that if you repeat this experiment with reddish light, this effect does not occur. It only occurs for bluish and ultraviolet light. Moreover, the electron ejection occurs regardless of the light intensity or duration of the time exposure. It was Einstein who understood in 1905 that Planck's law actually has to be interpreted such that light comes in quanta, or countable amount, of energy. We call these quanta photons. The energy of a single quantum is described by the product of its frequency and Planck's constant. The photon frequency is related to its wavelength through the speed of light. There are a number of units in which the photon energy and wavelength can be expressed. In the field of photovoltaics, we generally express the energy in electron volts, which is equal to the energy of one electron moving across a potential difference of 1 volt. 1 electron volt therefore equals 1.6 times 10 to the power minus 19 joules. The wavelength is generally expressed in nanometers. The Planck constant times the speed of light, expressed in electron volts and nanometers, equals 1240 electron volt nanometer. This number can be used to relate the photon energy to its wavelength. The wavelength and energy of light strongly affect how photons interact with matter and even how we perceive them. If we look, for instance, at the visible spectrum, the arrow indicates the direction of increasing wavelength. The visible spectrum ranges from blue photons, which have a wavelength of about 400 nanometers, to red photons with a wavelength of about 700 nanometers. Photons with a wavelength smaller than 400 nanometers or greater than 700 nanometers are in the ultraviolet and infrared part of the spectrum respectively and are invisible to the naked eye. Since the photon energy and wavelength are inversely related, the arrow of the energy is pointed in the opposite direction. This means that red photons have a greater wavelength than blue photons, but are less energetic. We can find out how great the energy difference is by entering the photon wavelengths in the provided equation. we find that blue photons have an energy of 3.1 electron volt, while red photons have an energy of just 1.8 electron volts. The power output of solar cell depends, apart from its conversion efficiency, on the amount of energy incident on the surface of a cell. The illustration shows a radiant source, in this case our sun, emitting light. Some of that light is incident on the surface A of a solar module. The total energy flux from the radiant source that is incident on the surface of the solar module is known as the incident power. The incident power is measured in watts. The irradiance, or incident power density, is the total incident power per unit area. It is therefore measured in watt per square meter. By integrating the irradiance over the entire surface area, we obtain the total incident power. We just discussed that blue photons are more energetic than red photons. Furthermore, not all photon wavelengths are emitted equally by the sun. We are therefore often interested in the power per unit wavelength. The term spectral is added to express a certain quantity per unit wavelength. Consequently, the incident power density per unit wavelength is called spectral power density or spectral irradiance. It is measured in watt per square meter per nanometer. We can obtain the irradiance from the spectral power density by integrating over the relevant wavelength range. Light incident on the solar module surface can also be expressed as a flux of photons, rather than a flux of energy. The photon flux is defined as the incident number of photons per unit area per unit time. It is measured in photons per second per square meter. The spectral photon flux gives the photon flux per unit wavelength. The spectral photon flux is related to the spectral power density through the photon energy. Indeed, the number of photons of a certain wavelength incident on a surface per unit time multiplied by the energy of a single photon gives the energy incident on its surface per unit time. As we recall, incident energy per unit time is the very definition of power. Integrating the photon flux and photon energies over all relevant wavelength range provides a total power incident on a surface. Let's try to visualize these definitions of light incident on a surface. If we start with the AM 1.5 spectral photon flux that is emitted by the sun and incident on the surface of the Earth. The spectral photon flux is given in 10 to the power 18 photons per second per square meter per nanometer. We can obtain the spectral power density from the spectral photon flux by multiplying the number of photons of a certain wavelength by the energy of a photon. With Planck's constant and the speed of light, we can calculate the photon energy from the photon wavelength. Here, the photon energy is given in 10 to the power 19 joules per nanometer. The blue line represents the spectral power density and is the product of the spectral photon flux and the photon energy. Due to the highly energetic lower wavelength photons, the highest power density of the AM 1.5 spectrum occurs in the visible 400 to 700 nanometer region rather than the 600 to 900 nanometer region where the highest photon flux occurs. We can obtain the irradiance from the spectral power density by integrating over the full wavelength range. The irradiance, integrated from 300 nanometers to the wavelength indicated on the horizontal axis, is depicted by the green line. As we can see, the irradiance integrated over the full solar spectrum equals 1000 watt per square meter, which is called 1 sun illumination and corresponds to the typical standard test conditions. Now, in summary, we have discussed the photoelectric effect, which demonstrates the wave-particle duality of light. We saw how the energy and wavelength of photons are inversely related and that a conversion factor of 1240 can be used to relate the energy and wavelength in electron volts and nanometers. We defined a number of ways to describe and quantify the amount of light incident on a surface. Finally, we illustrated the relation between the photon flux, energy and irradiance. We are now ready for the optical losses in solar cells, which will be discussed in the next video.